All right, this is it. We're at the end here. I'm just going to wrap up chapter 14 on simple harmonic motion. So this will be the last lecture. When we introduced simple harmonic motion, we just kind of said, hey, let's try to use a cosine and sine function. And we kind of justified it conceptually why you can use a sine and cosine and model the simple harmonic motion, but it's always nice to be able to say mathematically why you can do it. So if I take the example of the spring, you stretch a spring out and the mass oscillates back and forth about the equilibrium point, transferring potential energy to kinetic back and forth, back and forth. Now, we can go ahead and look at the force that's being exerted at any given moment. It's given by Hooke's law, minus k delta x. And we're going to use a coordinate system here that automatically references the equilibrium position to be 0, so we'll just call delta x x, since the initial is always going to be 0. And if that's the only force that acts on the object, that's equal to ma. Now, this is a type of acceleration that we don't typically deal with because it is not a constant acceleration. The acceleration depends upon the position. So there's like this cyclic nature to how parameters are determined here. The position determines acceleration, which determines how much your speed changes, which determines how much your position changes over and over and over again. And when you have behavior that acts that way, that seems to be sort of cyclical in how parameters are determined, that's ultimately what a differential equation is. As if we write the acceleration in terms of the time derivatives of position, we get this differential equation here. The second derivative of x with respect to time is equal to minus k over m times x. This is a rather simple differential equation, probably some of the easiest you can get. I mean, the solution is basically what functions, when you take the second derivative of them, give you back the same functions, with maybe a constant in the front. And sines and cosines satisfy that relationship. Now you got to take two of those derivatives, so you actually get two factors of radical k over m, which is ultimately related to omega. And so that's basically mathematically why this stuff works. And here you can make the connection with k and m being parts of what we call the equation of motion determining the period of that motion. It's the proportionality between the position and the acceleration, so it makes sense that those numbers are going to be related to period. So anyway, this equation that you see down here, okay, the second derivative of position in time, this is what we call the equation of motion. And it is generally some kind of differential equation that you have to solve in order to understand how the position, velocity, and acceleration work in the object. So you'll see a couple of these today. But this is some higher level stuff, mathematically speaking. When you get into junior level physics, you start looking more at equations of motion, and you start looking at operators and spaces, and then it gets really kind of a little abstract mathematically. But I'll show you some examples here, but ultimately you want to solve for your equation of motion. Okay, so if you solve the equation of motion for a constant acceleration, you get the kinematic equations that you know. That's the solution to like projectile motion. That's the solution to any kind of constant acceleration. This is not a constant acceleration. The equation of motion looks different, has different solutions. So, all right. So we're going to apply this in a lot of different ways. We talked a bit about horizontal oscillations. We can talk about vertical ones. Now, vertical ones are seemingly more complicated because now they involve an additional force, and that's the force of gravity. So we want to sort of analyze the equation of motion here and try to determine if those same things are going to apply if things are vertically, if there's an additional force in there. Let me get back to my slide here. Okay, so the idea is that you have this spring in here, and the weight of the object that's attached to the spring is going to give out this initial stretch, and that's determined by just setting Hooke's law equal to the force of gravity. When those are in equilibrium, that's so you can figure out what the delta L is. Delta L being how much it's stretched out from what it would be if it didn't have a mass attached to it. Right. So let's do a problem or two involving this. Let's jump to my example here. Okay, so we got a spring hanging from a ceiling. Attaching a ½ kilogram physics book to the spring caused this stretch 20 centimeters. So that's our delta L in order to come to equilibrium. From equilibrium, the book is then pulled down 10 centimeters and released. We want to know all these different parameters here. Right, so the relationship for a vertical spring here is that the stretched out equilibrium position is given by mg over k. So we rearrange this to solve for k. We put our numbers in there, make sure everything's SI. 24.5 newtons per meter is what we get for the spring constant. If we want to figure out what the period is, we can use the relationship we learned that relates the period to the mass and the spring constant. So that's this T equals 2 pi radical m over k. Remember, this only works for springs because it involves the mass and spring constant here. There's different forms of this if you have different kind of oscillating systems. Plug our values into here, we get a period of 0.9 seconds. Max speed, again, we have tons and tons of little equations all throughout this chapter here, so we just got to dig through the one that gets us what we need here. And Vmax is omega A. Omega is given by a radical k over m. And so we'll put all those numbers in, we get out 70 centimeters per second. So it's a pretty straightforward problem, but you got to remember all the little equations. And so that's the challenging part, really, of something like this. All right, move on. Okay, we got this block now oscillating on a vertical spring. When the block is at its lowest point of the oscillation, what is the acceleration going to be? Think about that for a minute. The answer here is positive. Right? So when it's at its lowest point, okay, all the way at the bottom, it's going to have its highest acceleration. Remember, the position and the acceleration graphs are, because it's the second time derivative, they're identical trig functions with a difference in being there's a negative sign in one and not the other one. So here, when you're at your lowest position, which you can call negative y, you're going to have your greatest acceleration. Right? So if you remember in the last lecture, we looked at like the relationships between position and velocity, trying to understand different points when things peak. Well, you can do the same thing with acceleration. Being that it's two time derivatives, it returns the original function. So if it's a cosine, except there's a negative sign in there. So everything is flipped in terms of signs. So when this block goes up, it'll have a positive position, but at that point it'll be slowing down, and that means the acceleration will change and start to go down. When the spring is compressed, force will then be downward, and so anyway, you can just go on and on about this, but okay. Okay, another type of oscillating system that involves the equation of motion is pendulums, and we've covered pendulums in the class sort of before. We did a lab that involved some pendulum work, and we had a relationship for period, how it relates to the length of the pendulum and the gravitational constant, but we really didn't go into the theory behind it, why the equation works, things like that. So let's go ahead and analyze this. At the bottom right, you have a free body diagram, but this free body diagram is given in the coordinate systems that we use for circular motion, because if we have small oscillations in our oscillator here, then it does resemble circular motion. So we have tension in the r direction, we have a component of gravity in the r direction, and we have a component of gravity along the t direction, which is along the arc that it travels along. So it's the tangential direction. And so the acceleration that the object's going to experience is going to be along the t direction, so we want to create an equation of motion along the direction. So the force is going to be mg sine theta. We set it equal to ma. You can divide the m's out of the equation here, and then we end up with this equation at the bottom here, which is our equation of motion, but got a couple issues with this one. First of all, we have an s and we also have a theta in here. And that's two different variables, so we're going to have to rewrite them, which we can very easily do because we used the arc length formula for that. It's L times theta equals S. But the other issue we have is that we're not going to end up with an equation like we did before, where the second time derivative of a function returns the function. This is the second time derivative of the arc length returns a set function, not the same function, but apparently returns minus g sine theta. And, given what the original function is going to be, this is going to be difficult to find a solution to this. So we got to rewrite some things here. As you again might remember from the lab, we use something called the small angle approximation to simplify this. If your pendulum has small oscillations, small amplitudes in its angle, then we can get by saying that the sine function is approximated by the angle itself in radians. This is true. You can check in your calculator 5 degrees, 10 degrees, 15 degrees. If you check the sine function in those different angles there and you compare it to what the angle measures in radians, they're extremely close to each other. And they stay very close within 10 degrees, and there's still a good approximation of the 20. So as long as you're adhering to a small angle approximation, you can cheat a little here and rewrite your equation of motion. So it's just in terms of theta, and of course then now here we take our theta and write it in terms of the arc length formula. So now we have this minus mg over L times S, which can be put back into the equation down here. And there you go, you got your equation of motion, and it has the solutions that match the stuff we did for springs. So we know that we can use our sines and cosines and all the other rules we learned. The only difference is that when you take those two derivatives, that's always equal to omega squared, by the way. When you look at your equation of motion, and the omega that occurs in the argument of the sine or the cosines, it comes out twice because of two derivatives. And so whatever sits out front in that equation of motion must be what omega squared is. And so in this case, we have a different form for omega than we did for springs. Remember, for springs it was k over m. This is g over L. So this is going to determine for us, what determines the period of this oscillation. And again, from lab, it's only gravitational acceleration and the length of the pendulum. All right, let's get to a problem. Okay, we got a ball, 0.2 kilograms. Don't care about that. Got to pulled to an angle of 8 degrees. That's okay. We're under 10. We're using a stopwatch. We find that 10 oscillations take 12 seconds. That gives us the period. So it would be 12 over 10, 1.2. How long is the string? So our equation to figure out the period is it's always going to be t equals 2 pi over omega. You just got to put in the appropriate omega. So when you put that in here, you end up getting that the period is 2 pi radical L over g. We rearrange the equation and solve for L. We get 0.36 meters. Okay. We want to know what the maximum speed of the ball is, and so we're using the same equations. It's going to be omega A. A is the amplitude, the positional amplitude, which is an arc length. So we're really asking what's the maximum arc length here, which again we want to turn that into an angle and a radius. So this is now omega theta max times L. For theta max it would be 8 degrees, but every time theta exists outside of the trig functions, you got to make sure you're doing things in radians. You cannot do things in with degrees here. So putting all those numbers in there, we end up with a 26 centimeter per second maximum speed, and that occurs obviously right in the center. Okay, there's as the pendulum oscillates, there's a energy transformation from potential to kinetic, and so this max speed's occurring right at the bottom of the arc where it's moving the fastest. All right, chugging along here. So, ball on a massless rigid rod oscillates as a simple pendulum with a period of 2 seconds. The balls are placed with another ball having twice the mass. The period will be, oh, look at, oops, didn't notice I clicked ahead too quickly. But, I mean, we've established this in the lab and said it a couple times already here. Masses doesn't really matter here. You see what the period is dependent on. It's basically dependent on the length of the pendulum. also kind of depends on being on Earth, but if you're somewhere else, you can replace that. Oh, look, we're somewhere else now, planet X. Okay, so we got on planet X, got a period of 2 seconds. If we take it to the moon, planet X, where the free fall acceleration is half as big, the period to be what? Okay, so think about what the equation is there. So remember that G, in terms of the period equation, shows up in the denominator, right? So if you got G over 2, the 2 actually comes up to the numerator. Square root of 2, it's going to be square root of 2 longer. And so that's why I get 2.8 here. So the period varies as 1 over radical G. So kind of makes sense, right? If gravity's not strong, this thing is not going to move as fast. Makes sense, right? All right. This is a pretty straightforward problem here. We're on Mars. Mars has about a third the gravity on the Earth. I think that's what they're asking for here. Yeah, that's what they're asking for here. So we're proving here. Well, assuming we've been on Mars, and we do this little pendulum experiment here on Earth, the pendulum has a period of 1.5 seconds. On Mars, it's slower, 2.45 seconds. Based on those two numbers there, can we measure the free fall acceleration on Mars? Well, this actually would be a very simple experiment for people to go to Mars. To measure this stuff is very simple. Yeah, you have a set pendulum on Earth, and you bring it to Mars, and you see the differences. So what's the same about the period? What's the same about the pendulum is it has the same length. So you can create a proportion. I mean, most of you are probably just going to take that period in there and solve for L, and then put L into an equation that you use for Mars, which is fine. You can do that. I like to play with my equations before I put numbers into them. So you can create a proportion out of this, and the proportion is the gravitational acceleration on Earth times the period squared is the same quantity on Mars, and so you can put those numbers in there. I like the proportion because you can kind of see how the gravitational acceleration is altered. It's altered by a ratio of squares of the periods. That's neat. That's neat. Right, anyway, 3.67 meters per second squared looks like is what we get for gravitational acceleration on Mars. Okay. All right, another application is what we call the physical pendulum. And with the physical pendulum, it's a sort of a more realistic picture of what's going on with the pendulum. Typically when we do our pendulums, it's a big mass on a massless string. It's the very end. And the reason we do that is because the free body diagram looks a particular way. Right? It's very easy to do a point mass, but most pendulums are more realistic, and we call them physical pendulums. And the reason why they would move would be due to the gravitational torque. Okay, so assuming that they're anchored down somewhere, they got a true pivot or axle, something like that, they won't have translational motion in terms of the object won't fall, but it will swing back and forth. And so we'll model that with gravitational torque here. And so you got to keep the same sort of small angle approximation. But what we're looking to do here is we're looking to say that that the torque is this is what the gravitational torque is, right? So gravitational torque, as we learned, is minus mgx, where, and in this problem here we call d. D is the moment arm here. But if you turn that into in terms of the angle, you can relate it with the sine function. So that d is going to be L, which is the distance from where the pivot is to where the center of mass is. That's like the hypotenuse of this triangle here, times sine theta. And then we make the approximation that sine theta is theta, and so we end up with the relationship that you see right here for torque. We set equal to Newton's second law, so that's I alpha, and alpha is the second derivative of the angle with respect to time. So we have our standard equation of motion, just like we did for the spring and just like we did for the normal pendulum. So one thing that would be a good exercise to do here is to work this out. Start from what gravitational torque is, verify that this torque is true, right? Set equal to moment inertia times alpha, rewrite alpha in terms of second derivative, rearrange it so it looks like the equation of motion, and then you will see what sits in the front of that theta there. That's omega squared. And so you can also verify that this equation down here is true that the angular frequency, and therefore a way to get the period, is to know a few things about how much mass is here and how it's distributed. So the m here is obviously the mass of the object. L is from the pivot to the center of mass. So it's one thing you need to be aware of when you solve these problems here, is that L is not necessarily the length of the object. It's just from the pivot to the center of mass. So you got to know what that is. And that can be easily confused with another distance that will probably show up in some sort of moment of inertia formula. If this is a rod, we know of two moment of inertia formulas for rods. If it's through the end, it's 1/3 ml squared. If it's through the middle, well, it's 1/12, but then if it's through the middle, we're not going to have much of a gravitational torque, are we? But then we did work out an equation. If you remember way back when I introduced this stuff, I actually did an integration, and we worked out what the moment of inertia would be at any distance along the pivot there. So if you really needed to, you can go back to that equation, figure out what those moment inertias are. I think I have probably a problem right off the bat here. I sure do. Let's get to it. All right. Okay, so a student in a biomechanics lab measures the length of his leg from hip to heel. Hip to heel. Okay, hip to heel to be 0.9 meters. That seems long, but okay. Is that long? I don't know. What's the frequency of the pendulum motion of the student's leg? What's the period? All right. So I guess the implication here is that your hip's going to be the pivot here, right? So if we want to solve for the period, I'll get the period first, we'll get frequency later. It's going to be 2 pi over omega. We know what omega is for a physical pendulum. This is going to be a physical pendulum. It's an extended object. So omega is, well, it's going to be 2 pi over omega. So when you put thing for omega there and you rearrange it, you're going to have radical I, GM, LCM. Okay, so this is a rod through one end, so we know that our moment inertia is going to be 1/3 ml squared. Okay, and the center of mass is going to be, we're going to assume the center of mass is the literal center of this person's leg. I mean, it's not, probably, but it's a good fair approximation. Although you can see when we put the numbers in here, we can go back and say, well, let's say it's a bit higher, because it is a bit higher, right? How would that change the problem here? So let's see. Anyway, plug all the numbers in. Mass drops out, right? And I thought an L dropped out somewhere here, but because there's an L squared. There's only one L in the distance there. So anyway, we end up with radical 2L over 3G when we clean it up. Put our numbers in there, we get 1.6 seconds. And of course, the frequency is simply the reciprocal of that, so 0.64 hertz. Now, kind of mentioned this thing. What if the true center of mass of this? Because I think modeling the student's leg to be a rod about one end is pretty good. I mean, your hip is pretty much the axle. Again, that is for a uniformly distributed rod, so it may be a little lower than 1/3 actually, because if more mass is distributed toward the hip, you could have a smaller moment of inertia. So the actual number may be maybe 3/10 or something like that, maybe a little bit lower. But then also your value for the L center of mass is going to be lower too. And the L center of mass occurs in the denominator here. So what that means is if the actual center of mass is a bit closer in, we're going to have a smaller number there, which is going to drive up the value of the period. So the leg would actually swing a little bit slower, looks like here, I guess. Anyway, that's what's nice about looking at those equations. Let's move on. Oh, sleepy. What am I doing here? Oh, okay. So we got a solid disc and a circular hoop at the same radius, same mass. Their pivot's going to be at the top, and they're going to swim as a pendulum. You want to know which one has a larger period of oscillation. So think about this real good. You may want to go back and look up what that equation was again. How does the period and the moment of inertia vary? Okay. So the larger period of oscillation is going to be the circular hoop. Why? Okay, well, the period is directly related to the square root of I. So if you look through the equation, you'll see that. And what has a greater moment of inertia? The circular hoop does. The moment of inertia of the circular hoop is, well, through the centers is mr squared. For the disk, it's 1/2 mr squared. We have to then use the parallel axis theorem to figure out what the moment of inertia would be through the tops of them. And so you would have to add in an mr squared to offset from it being in the center upwards. But you're adding the same constant anyway. You still find that the circular hoop has a large moment of inertia. So if you oscillate them, if you kind of kick them, let them oscillate, the disk is going to go a little faster, and that hoop's going to go a bit slower. All right, well, let's see here. I wasn't really going to go over damped oscillations. You may, if you're curious, I'll keep talking here, but if you're just done with this stuff, you can stop here. But there is one more little topic I want to talk about that's just interesting, really. I don't think I'm going to give you any problems related to this in the homework on the test, but it's a nice thing to see and gives you kind of a glimpse of some higher level physics stuff. Damped oscillations are oscillations that experience a dissipative element to them, and it causes their amplitudes to decrease in time, which obviously is a more realistic picture of any oscillating system. Every oscillating system has some damping coefficient to it. And we've talked a little bit about how to do drag. One of the things we learned is drag is proportional to the velocity of the object. So if you want to consider equation of motion stuff and you're looking at a, say, I don't know, let's talk about the block on a spring. As it's oscillating back and forth, it's going to be experiencing a constant, well, not a constant, but a continuous drag force on it. But the drag force is proportional to the velocity of the object. And of course, the velocity changes as the object oscillates, right? It gets lower as you get further away. It's higher when you get close to the center. So your equation of motion is what we have in the bottom here. You have minus kx, which is the force due to the spring. You got your minus bv. B is what we call the damping coefficient. It's just how effective drag is. And that equals ma. Well, this is a lovely differential equation. It's a second order differential equation. It does have a first order term in it. And now we're getting to higher level stuff here, and this doesn't have an obvious solution to it. The solutions do exist, and so if you can solve that equation of motion down there, you get the following equation here. So a bit more complicated for sure. If you want to learn how you go from the last slide to this slide, well, that will be differential equations that you'll take at some point, or not. Maybe if you're not going to need to go that far. But what are we looking at here? You're looking at a position function that is still sinusoidal. You still see a cosine in there. You got omega t, you got our phase shift. But if you notice, the coefficient is an exponential decay. So the way you should think about this is the oscillatory motion is still here, but it is modified. It has what we call an envelope to it. And the envelope is an equation that expresses how the amplitude decays in time. The value for omega here is a bit more complicated in order to actually solve that differential equation there. It looks like the familiar k over m that you know, but there's a factor here that involves a damping coefficient. So this is basically saying that the drag is driving the angular frequency down, depending on what the values of mass and the oscillator, the damping coefficient is like. Well, here's the envelope I talked about. That's exactly what that equation looks like. You can still see the cosine function there, but it has this exponential decay envelope onto it, and so that's how we model